Okay, then let's continue with neurocognitive methods, and in this case magnetic resonance imaging, and more specifically continuing our explorations of the magnetic moment dynamics from last time. So I hope you still remember that we're talking about this dynamical model for the net magnetization of a small spatial unit in some sample, and that we so we're talking about magnetic moment dynamics, and specifically the net magnetization of a small spatial unit in the presence of a strong magnetic field which is oriented along the z-axis. So we have this very strong magnetic field that is generated by the MR scanner and points along the z-axis. So that's that. And I hope you remember that we discuss the dynamics of some magnetic moment vector, and we have established essentially by now that this magnetic moment vector is the dynamics of this as given in terms of systems of differential equations. And in very short notation, this can be written like this. So it's the cross product of, so the rate of change of this vector is given by the cross product of its current state m and the magnetic field. And the intuition behind that was, or some intuition behind that was, that the rate of change is always orthogonal to the plane given by the magnetic field and the magnetic vector, and there is some decay which now also fairly unspecifically you can write as a kind of, although there are different time constants for the different components, as that the rate of change is always decreasing as a function of the current state. So this is essentially what we discussed last time. So if one looks at this in a little bit more detail and one actually computes the cross product, then one gets the following system of differential equations. So mx, my, and mz being the components, of course, of this vector. So the three numbers that you need to specify the head of this arrow, if you represent it as an arrow, or just the point, if you just think about the three numbers in it themselves. These three numbers and the rate of change, if one computes the cross product, as we did last time, are then given by my times, and this comes in from the magnetic field, where we established that there is a static magnetic field along the z direction, which is called B0. If one multiplies this with the gyromagnetic constant gamma, then we get this omega 0 plus the gyromagnetic constant and this space and time varying magnetic field minus the T2 time constant of mx, and here minus mx times the same thing And so these two differential equations being coupled in the sense that the rate of change of x depends on the state of y, and mz not being dependent on the other two. So mz just being dependent on itself. So what I suppressed for now is the dependency of all of these mx, y, and z's on space and time. The reason that I suppressed them now is that it's then, of course, a little bit easier to see what's going on. On the other hand, it's also maybe not easier to see in the sense that one doesn't appreciate that this is different, that this varies depending on location, which is in here also, and this, of course, that these things, so my, mx, and mz are all functions of time, which is inherent in the thing that in the thing that this whole thing is a dynamical system. Yeah, so you know that all of them. If you look, for example, at 41.7 in the script, that the components of M, they all are functions of space R and time t, and the T1 and T2 time constants, they are functions of space. Yeah? So at different locations, you have different time constants. Otherwise, the whole imaging business would not work. So essentially, this is where we got up to, and I already said that these are essentially two ways of trying to establish that this magnetic moment vector does this decaying precession upon excitation. And the first thing that I want to look at today is kind of the third way to look at that, namely in terms of the solution of these differential equations. Yeah? So that then once you have, if you have the solution, then essentially you can, without using some integration scheme like Euler methods, you can just plot the solution and look at it. Yeah? And that's the first thing that I want to do. And then we can look at the solution also. And then the next thing would be to talk about gradients. So that's the first plan today. Solution and gradients. Are there questions right now before we start with that? No. Okay. Yeah, and the motivation behind this, of course, still being that we want to understand how this imaging thing works, so that we can use these moment dynamics and playing with these magnetic fields to create an image of the brain, right? So we're not doing this because it's so cool to write down a lot of mathematical equations and then try to understand them, but we're trying to understand how the freaking MRI scanner works. Yeah? Don't forget this. Good. And believe me, because I've now maybe a little bit ahead of you in studying this, it actually works and it pays off to do these things. Otherwise, I wouldn't do that. Okay, so the first thing is about the solution. And do you remember how we established, forget the question. So the way we looked at solutions of differential equations previously was to not develop kind of methods to analytically derive solutions to differential equations, which one can do, and it's of course a mathematical field, although it's maybe becoming less and less important the more easy it gets to just numerically compute solutions. This is not what we did, but we basically just checked that certain things that we guessed could be a solution are solutions. And in this kind of setting, I will now try to present solutions to this system of differential equations. Yeah. So this is our system of differential equations, and now I will write down a solution, And then we check that this is actually a solution, and then we are happy and go to the next thing. We don't study how we come up with this solution in the first place. Yeah? Because that's not what we do right now. Good, so the solution to this system of differential equations, now again with the dependencies, I think it doesn't hurt to put them in. So the solution are actually the following. So the solution for some initial conditions, so we need an initial condition, which will actually become very important later on. So the initial condition is that the magnetic moment at location R at time point 0 is given by 3 values, mxr, myr, and mzr. Just as a thing for the future, this will actually be encode the image. Yeah? So the question is, what is the magnetization after excitation, which is, of course, if you do proton density imaging, given by the relative abundance of protons in your sample, and you can basically use this as a for your image formation. Yeah? So this will take center stage at one point, but not today. Today it's more the initial condition, which we of course need for the definition of a solution of a differential equation, if we don't want just have a very general solution. So the solution then takes the form of a exponential with decay. I always wonder, if I write something like this down, do you have a function in mind? Can anyone, do you see what this actually represents? No? Then we go over that in a second. The other one, we will also go about in more detail. So the next part is relates more, so this exponential decay actually comes in from this minus mx. This coupling of the mx and my component results in this beauty here. So we need an integral of the gradient over time, which is actually very important for the whole imaging process. So I wouldn't put it here if we wouldn't need it. Plus myr sine omega 0 t plus gamma t0 delta b r tau d tau. And I think I actually will, of course, you see that this is kind of on page, what page is it? Page 3, it's actually a page full of equations, so it's not that conceptually interesting. So I will only present the solution for essentially this mx and the other ones. So the my solution is essentially the same as the mx solution, but with x and y and a minus sign exchange. And the solution for the z is just an exponential decay. So so that we don't do things here then just for fun, but over this I will go with in some detail. So maybe first, with respect, before we go into the derivation, with respect to the exponential decay. So exponential decays have this kind of form. So the t, so you know how the exponential function looks. So the exponential function this as a kind of x-course exponential decay. This is actually something that I studied a long time. I remember studying this when I was in Tübingen, and we discussed neurophysiology and action potentials and so on. So this is stuff in the back of the Kandel book, if you're interested. So an exponential decay in general has this kind of form. The exponential function, this is just the exponential, of course, looks like this, where so this is not the exponential decay, this is the exponential function, where the exponential of 0 is 1. Now, if time is positive and we are we have a negative sign in front of it, then of course we look at this part here of the exponential function. So, but of course time is positive, so we essentially flip the script. It's very old school. So that's not very nice. So essentially we have something like this, and the rate of this decay, so this is just this flipped now for positive time because we have a negative sign in front of it. And then the tau, that is the time constant, and this refers to the time when the initial value of the exponential function has decayed to one. Let's just do it, because it's either 63% of its initial value or 27% of its initial value, depending on how we look at it. So the point is, if you look at this, that's 1. If you look at this, that is exponential of -1. So this is 1 over 2.71, which must be 30. What is this? 37%? 63? 37? Can somebody just compute this? Must be 37 something.
Yeah, 37%.
So it's the and of course this now started at being multiplied here with 1. Of course that could be starting from something else, but this factor would also be always be this. So the time constant tau is a measure of when in time the original value has decayed to 37% of its original value, or has decayed by 63%. Yeah? It's kind of high school stuff.
Again, please.
So tau measures, so tau is a time constant, and it measures when the initial value that this function has decayed to 37% of its initial value. Yeah. So tau can of course change. So this is when things are at 1, and at one point we are at 37 of it, and then this happens at a thing called at a time called tau. And depending on how what the value of tau is, this happens either earlier or later. Yeah, so that's another tau here. It's a longer time constant. So this is the notion of time constants in actually all of this dynamical systems business, and especially if you're dealing with exponentials. So T1 and T2 time constants, they measure when the initial value has decayed to 37% of its initial value. Yeah, that's good to know. Although I always just remember something about 37 or 63 of something. But it's quite easy because it's 0 is 1, and then if you put in tau as the argument, so at time point tau, then of course you have exponential of 1, which is 2.71, because you know that because that's Euler's number. So why did we do that? Because in the solution for the x component, there is an exponential decay. So what we already then know about this whole thing is that there is some, that the x component decays. So it starts out maybe large, and then over time, depending on the T2 time constant, gets smaller and smaller. The other question is, of course, where does that come from? And as the third question is, where does all this stuff come from, and what does it mean? And that's then the next thing after this little tubing X course. Yep.
On the right side, does it say 1 minus or 1 is equal? Or?
This here?
Yes.
No, this was times. That's times, because if you use just the exponential function, it always starts at 1, because if you put 0 into the exponential function, you get 1. But you can, of course, multiply the exponential function with some value, let's call that a, and then your initial value is not always only 1, but it can be 10, and then you go to 3.7 after 1 time constant and so on. Yeah. Other questions? Good. Then let's look. Now, actually, we need both of them. So after this, let's write down again our solutions and then prove this solution for x, because we actually need the version for y as well. So let me write this up again. Cos omega 0 t plus an integral So that's the solution for x, and to actually relate this to our differential equation system, we also need to at least write down the solution for y. We don't need to prove it, but we need to write it down. So this starts with my r, and then cos omega 0 t plus gamma. This integral of the field, this will be, as I said earlier, quite important. And oops, there's a minus sign. So, and now the thing that you can do with these solutions is either wonder how somebody came up with them, or basically clarify for yourself why they solve this, and then be happy and go on with your life. This is the latter is what we are doing, and to do that, I will not always write down this dependency on R, because we appreciate that this is all dependent on R, but we now not write it out, because then we have to write a lot. And so that's kind of the straightforward thing. The other thing that is helpful in terms of notation is to, because this term here is a little bit longish, to express this as a function omega t. So this we just summarize as omega 0 t plus gamma gamma times our field, where we also suppress the dependency on R and only keep the tau in. Yeah. So essentially, we just summarize this business here as omega t, so that we don't have to write that much. Yeah. That means now if we want to check that this is actually a solution, so check that this is a solution here, that this business is a solution. We essentially just have to compute its derivative and see whether this in some meaningful sense relates to our differential equations system and the solution that we have for my. And that's quite straightforward, so let's do it. Before we do that, we already know that we will have to take derivatives with respect to time, and we have this omega t in there, so we might as well already look at the derivative of omega t with respect to time. Then we already know it and don't have to do it afterwards. So our d dt omega t is, by the linearity of differentiation, it's omega t plus dt of can put the gamma up front already, this thing. So what's the derivative of this? Omega 0 times t, and you compute the derivative with respect to t. 1, not quite. Also not quite. Omega 0, yeah. So the derivative of t is 1, that's true, but there's so it's essentially 2x, and you compute the derivative with respect to x. So then you have 2. So you get omega 0. And this is a little bit more tricky. It's fairly intuitive if you think about it, and we actually discussed it in the very beginning of the course. And it's actually also, there's a proof of this whole thing also in PMFN. Any suggestions? I mean, you have it in the script, but maybe that you can in some way explain this derivative here. What falls out of it? Somebody who looked at it? No? So the intuitive way to see this is that this is the so this integral from 0 to 10 to t, sorry, of delta b t, or tau in this case, because we need an integration variable. This is the antiderivative Stammfunktion of the function delta bt. Yeah. So if you look at this as antiderivative of delta bt, Stammfunktion of delta bt, and you take the derivative of the Stammfunktion, the antiderivative, what do you get?
Delta bt.
Yeah, so you get the function itself. So this looks from, if one looks at the formula, okay, it looks a little bit complex. So you have an integral sign and you have a d dt, but intuitively this is Stammfunktion. So you know that if you want to compute an integral, you need to compute the Stammfunktion, which is this antiderivative, and you know that to the Stammfunktion, if you compute the derivative, the original function must come out. So this is what's happening here. There is a justification, a formal justification of this also in PMNFN early on, so that one looks at this a little bit more formally, that this actually works. But in one can also be quite happy with that fairly easily. So, and now we already have this d omega dt, as the derivative of omega t, which we will need later. So now we can compute the derivative of the solution, and this, the reason why I'm doing this in some detail is to basically show you that if one goes into the details, there's nothing complex about this whole thing. It only is complex as long as one doesn't go into the details, because then it's unclear where all these things come from. But if one goes into the details, it's just derivatives of simple things.
Excuse me, I do have a question regarding the t and the tau. So now we were talking about the delta b t or tau?
Okay, so this is the tau is just the integration constant. So what the solution says, so the solution says there is something in there that is the function b integrated from 0 to t. Yeah, because our function that we are looking at depends on t. Yeah? So that's not correct what I'm writing here, but the function depends on t, and its dependence on t in the solution is parameterized or whatever expressed, or the functional form is that it's the upper boundary of this integral. And this integral is over the function b t, which is a function of time. But if you, so in general, you call the input argument, or I call the input argument t. But if you now have the thing that the upper boundary is actually this t, the dependence here, it makes sense to not write this because it's confusing. Like this morning when we exchange indices, just call this tau. Because this is just a number, it's, the integral is just a number, and this is just the constant that is getting rid of once you compute the integral. This is the function that we usually call bt. But right now the t is importantly the upper boundary. Yeah? Now, in a simplified way, I've written down our solution. So instead of putting in the omega 0 t plus gamma integral delta b and so on, there's just omega t, and all the dependencies on r are suppressed. And there is one bracket missing. I've seen omega t. So, and now we have to compute the derivative of this, and this is a nice little exercise in basic calculus, which is always good to do because it's good for the soul. So there's a product of two functions of t. So what do we need if? So what calculus rule do we need if there's a product? Which rule do we need if there is a product? No. The product rule, exactly. Chain rule is always a good, so if you in terms of Bayesian statistics, chain rule is always a good prior. So you should have high probability for chain rule whenever you think what you need for a derivative, but sometimes you actually need other ones. So anyone remembering the product rule? So if you have something like this and you're supposed to compute the derivative, so essentially the derivative like this.
Wasn't it something like the derivative of f times g, and that time f
That maybe will help you.
Plus f times the derivative of g.
Exactly. That's the product rule. So this one can, and this is just what I spell out on the next spell out. So essentially, if you look into physics books or also in the Nishimura, these kind of calculations you never find in books because it's appreciated that everybody can do them themselves and we don't have to talk about them. But I like to actually write them up because then I think a little bit more about why this is working, and hence we are now discussing them. And I think it's helpful because you get more used to these equations and how these things work. So let's just write that up. So our f is now this first exponential of t, and our g is this. So we need to have the exponential of, the derivative of the exponential of this times our g, which is this. Which of course, if you do it using LaTeX or Word or whatever, you can just copy and paste and you don't always have to write it up again. Plus the f, which is our exponential, times the derivative of g, which is our longish cosinus omega whatever. So this is just application of the product rule. Then we of course have to go on with computing derivatives. So here we have the derivative of this exponential minus t2, which is a typical scenario for the chain rule. So briefly, chain rule, what is, if I, chain rule, of course, you have to do it this way around, it doesn't really matter. Derivative of a function of something, what's this?
It's derivative of f times g times derivative of g.
Almost, this is correct. But it's not times, so it's derivative of f
times g plus no.
So it's the derivative of f at the location of gx. That's how I hammered it into my brain. So it's derivative of f, and you put in the function gx. So at the location of gx times the derivative of g. Yeah? And that's always helpful if you have the exponential. So because the derivative of the exponential is what? The exponential. So what do I get then for this bit? If you look at this. So look at what it says. So you need to, of course, identify f and gx somehow in this expression x minus t2. So maybe let's do this a little bit as a little thing here. So the what is the outer function? So what is f? Yeah, can you be more explicit? And because exponential is correct, but you maybe?
No, I was going to say exponential.
Exponential?
The exponential function of t over.
Yeah, this is actually what I meant, because it's easier if you just say it's the exponential function of something, of x, for example. So that's our fx, and our gx is then what?
Minus t divided by t2. So
Minus t divided by t2, yeah. So minus x divided by t2. So yeah. And
minus 1 divided by t2.
minus 1?
So the derivative.
Yeah, the derivative, yeah. But for now we need these derivatives. Exponential what? Yeah. And this derivative, I think you already said it, now he's gone. Yeah. And now we have to still apply this. So what is then f prime g x g prime x?
Exponential of minus t over t2.
I'm using x now because we started with x, but yeah, you're right.
But, well, t would be the x.
Yeah, yeah.
Multiplied by minus 1.
Exactly. And of course, this can be replaced by t, but I started here because I want a different argument. So that's 1 over t2 with minus sign, which do we have that? No, I think we forgot it. Did you say it? I guess you said it. It needs a minus sign, of course, which we somehow we still have here, and then we lost, and times this. So so that's the derivative here, and with this little thing here, I'm basically showing that you can do it. You just need to do it. Yeah, so derivatives are not hard, and you all computed many of them in school. They are the same derivatives as always, but you need to, and they are specifically simple if you just follow the rules. Just establish the rules and then just follow them. So we have this, and then we still have our entire mx cos omega t plus my sin omega t plus our exp t divided by t2, and now we need to compute the derivative of this thing here, so this. So any suggestions? Now, let me help you. So we first need to, of course, compute the derivative of each term. So mx cos omega t plus dt my sin omega t. Yeah, so we have to compute, because of the linearity of differentiation, we have to compute the derivative of this and the derivative here, but they are fairly similar. Now you have the cosine at omega t, and omega t is a function that we already defined here, and we actually also already computed its derivative. So again, you have a function inside a function, which means you need to apply what? the chain rule. And if you do that, of course, you need to compute the derivative of the outer function. The outer function is for the first term, it's the cosine. What's the derivative of the cosine? Minus sign. And then you need to have this at the location of the inner function, which is just our omega t function. This is in omega t, and you have to multiply it with the derivative of the inner function. And this derivative we actually already computed. And for the moment, we can still leave it just implicitly like this. So we have, because we could either write it out or we leave it implicit, and we leave it implicit. And here we have actually the same thing. So of course we need to put in mx in front of it. So this is now this, and this derivative works identically, only that the derivative of sine is not sine, but it's cosine. So we have cos omega t times sine. We just have the derivative of sine is cosine, and times d dt omega t. And now I'm actually tired of writing things up, so we go on, because the rest is, I think it's easier to see if I just explain the equation. So we are currently here. Wait. Do something. Oh. That was maybe not the best idea. So we are currently here. Where we now computed the derivative of this mx cos omega t and my sin omega t, and then whether I write it down, I don't know. So this bit here in front, where we computed the derivative of the exponential times mx cos omega t my sin omega t, this is equal to what? Well, now this is sorry. This is equal to the. Now I'm confused. Sorry. This thing is where we started out. So we started out with this. This is our solution. This is our solution. Our mx. This thing. It just looks a little bit different because we have the integrals here. We started out computing the derivative of x minus t mx cos omega t. Now we found this again, but with a factor minus 1 t half, t2 in front of it. Yeah. So this long thing here, minus 1 over t2 x minus t2 mx cos omega t. This is where we actually started out. So our solution with a factor minus 1 over t2 in front of it. So here it's already the minus mxt. Now the second part, this is what we just computed. So we have our minus, let's make it a bit bigger. think so. So we have our minus mx sine omega 2 dt omega t my cosine omega dt omega t, which we just computed. Then what I'm doing in the next step here is just to put this latter part here in front. Yeah, so nothing else happens. The only thing that happens as well is that I take out the dt omega t. So this is isolated here, and I put this part into the back. Yeah, so this goes from here to there, and this dt omega t, this factor, which is both in this term and in this term, is taken out. The reason I'm doing this is that this x minus t over t2 my cos omega t mx sin omega t, this is our solution my. Yeah. Again, if you replace this business here with omega t, you have a cos of omega t minus an mx of the sine of omega t. So here we recover our myt, and we have, of course, need to still put in our dt omega t, which we computed here. So that's our omega 0 gamma delta bt, which we can put in here. And then, and this is now the crucial part, then we see that we have the solution myt, omega 0, or we have the derivative. The derivative of this solution is the my component minus the mx component, and this my component multiplied by omega 0 times gamma t. And this is what the differential equation system wants. Yeah. So if we use the solutions, again, let me remind you again of the logic. If we use the solutions that we proposed here, and we compute the derivative of the solution, we actually recover this form just by computing the derivatives. Yeah? So we have a solution for mx, compute the derivative. Turns out the derivative of the solution mx is the solution my minus 1 over t2, the solution mx, with a little bit of nitty-gritty calculus in between. So that means that the x component solution here, so this long thing, actually solves this differential equation. Yeah? Are you happy about this? Do you get the logic? Other questions?
Yeah, so just to get this straight, so we're computing the derivative basically to prove what we said in the beginning, that the rate of change of, for example, mx depends also on my.
Not quite. So, but it's good that you say it like this, because this is our modeling assumption. So this is how the model is specified. So the model says the rate of change is given by the cross product of the magnetic moment vector and the magnetic field, which implies the idea that the change is always orthogonal to this plane. So that's what the model says. That's the modeling assumption. This implies this system of differential equations, because when you compute the cross product, you get this. The question is, which kind of functions solve these differential equations? Yeah, that's always the question. Then we say, okay, let's test whether these functions here solve this differential equation. And then we test it. And by testing, we mean we compute the derivative and see whether we can recover this form of the derivatives. And by computing the derivative, which we started out on by hand, and then once we had the main things together, we went here. We see that actually these solutions, if you compute their derivatives, yield derivatives that in terms of the solutions have this form. This is exactly the same as we did for the exponential function when we did this. That's exactly the same logic when we did our x by x, and we found that a solution for this is this, but depends on some initial value. It's exactly the same logic. So I would really recommend that you look at how we establish solutions for differential equations in this very simple case, where you don't have like all this cos and mx and minus and sine and so on, and get the logic straight there, and then see the parallelity or the parallel aspect as it's used here, to basically just appreciate that these things here, which look a little bit daunting, but then also not that daunting, so these things are actually solutions. Yeah, just by computing their derivatives and identifying that the derivative of mx is then given by my rt times omega 0 plus gamma delta bt minus mx, which the differential equation system requires here. We confirm that these are solutions.
So these functions are solutions, or only their derivatives?
No, the functions are solutions for the differential equations. That's how the whole logic of differential equations. So that the solutions of differential equations are functions, like we did before Christmas. And these functions are solutions for the differential equations. And to see that they are, we compute the derivatives and see that they actually fulfill the requirements of the differential equations. That's the logic. The thing is, from an intuitive perspective, describing the whole thing in terms of the cross product, describing the whole thing in terms of the differential equations here, or describing them with the solutions of the differential equations here, it's always the same thing. It's always this precession decay, yeah? Which we will look at in a second, a little bit more after the break, I guess. So it's just three ways to essentially say the same thing. And you can find that annoying, but this is the thing that one has to deal with in terms of looking at the physics or mathematics of this in detail. And of course, the differential equations are somewhat more general than the solutions, because the solutions depend on initial conditions which you have to set in a given setting. And based on and the differential equations just say the rate of change is that, but they don't say if you start out here, then this and this happens, but they are more kind of on a meta level. They say the rate of change is always this. Of course, the problem is a little bit, as I also realized when I presented it, one gets a little bit into basic calculus details, and then one gets lost because, or can get lost. Yeah, that's a little bit the problem, but the thing is that also how you can then try to understand, and this is what we will do after the break, how you can look at to kind of intuitively appreciate what's happening. You can either use the differential equation form and use some numerical integration approach like Euler method, as we discussed before Christmas, to look at what's actually happening. Or you can use the solution where you don't have to use some numerical integration and just plot the function and look at what's happening. And this is what we do after the break to again look at what's happening. Yeah. So let's have a break and do another short bit after from 11:25 on.